I wanted to show my brother Art and anybody else that's interested, if anybody stumbles across this video, a couple spreadsheets that I developed for my ham radio hobby and my engineering work that I do on superhet transceivers occasionally, that type of thing, antenna projects, balun projects, unknown projects, that type of thing. So Art and anyone else, welcome to the amazing N8NK RF Toolz electronic numerical RF calculating machine. Okay, here's what I use. This first section, I'm just going to go through this thing section by section. This first section handles toroidal cores and variable inductors and balun cores. Okay, the first section is for powdered iron toroids. Let's say I need an inductor of 2.2 microhenries. I want to see what core would result in an even number of turns, if any. And that's generally how I do it. I'll pick the core. As long as it'll physically fit on my board, I'll pick the core that I have on hand that comes closest to the even number of turns. So let's say I need 2.2 microhenries, okay? A T37-2 core would require this many turns, which is not doable. So what I'll do, I'll just copy that, I'll paste it into the range of cores that I'm interested in looking at, and just like that, I have a listing of how many turns it would require on each of those cores to achieve that inductance. Just so happens that that one's almost an exact, you'd go with that one. But just for argument's sake, let's say this was the only core I had on hand, a T56, okay? 23.5 turns. I wonder what's my inductance going to be if I wind it with 23 turns, or conversely with 24 turns. And I see that I have this for an inductance, not 2.2 but 2.116 microhenries. Okay, that's what I use this first section for. I'm going to copy that and I'll show you why later. The next section, like I said, does the same thing, but these three are little variable inductors sold by Amidon Associates, and they're in a metal can. This is your garden variety, your common IF transformer in a can, used in HF radios all over the place. These are ferrite toroids that I typically will use for broadband transformers in a transceiver. This core through this core are ones that I would wind an unknown on, or a balun if I were into baluns. This one's the one that I'm currently testing right now. So anyway, what was I gonna? I'll show you one. I'll show you something that I've used this for. Okay. I've used it for a lot of things, but the most recent use. So this is the doubled core that I'm using for my unknown for 80 meters. I wondered, a lot of people wind them with a 2-turn primary, and this will show you how that can be problematic. I went with a 3-turn primary, and on that core, this is my primary inductance. I'm going to copy that. So we'll go down to the next section here. Let's look at this inductive reactance calculator. So with that 3-turn primary on that doubled FT140-43 core, I got that inductance, right? And it's for my 80 meter end bed. So let's look at 3.5 megahertz, the inductive reactance of that 3-turn primary is 333 ohms basically. Ideally, your load impedance will be 10 times your primary, your source impedance, to minimize loading effects. Well, that's workable. It's not 10 times, but it's workable. Look what happens if you wind the primary with 2 turns. The inductance drops to this, and if we figure the inductive reactance for that value, we can see that our inductive reactance for that primary on that unit is only 150 ohms, 148 ohms. Or as Buzz 1151 likes to say, ohms. So I use this inductive reactance calculator a lot actually. I had a need to figure an inductive reactance in the audio range, so I wrote range for that, millihenries and kilohertz. I wonder, 1 millihenry, 1 kilohertz. Whoops. Thanks, you. 6 ohms. Anyway, that's what that does. Capacitive reactance calculator, same thing. No need to go into that. LC resonance calculator, very handy. I use it a lot. Let's say I'm working on a circuit. I'm doing whatever I'm doing, and I see I've got an inductive reactance of 3.25 microhenries in parallel with 82 picofarads. And I wonder what the heck resonant frequency. That's where you might use that. Also for the audio range. What else? Let's say I want to develop a resonant tank circuit. I want to develop a trap. Let's say I've got a doorknob cap of 50 picofarads. No, that's a bad example. Let's say I've got a 2.25 microhenry inductor, and I want a trap tuned to just under the 40 meter band, okay? Let's say 6.9 megahertz. This will tell me how much capacitance I need to resonate at that frequency. What else? Return loss to VSWR. If you have almost no return loss, that means all your power is coming back. Let's say you've got 0.1 dB of return loss. Almost all your power is coming back. Your VSWR must be high, which it is. Conversely, if you have very, very high return loss, it means your system is lossy to the return of power toward the transmitter. It means you have a very high return loss. Let's say you've got, I don't know, 38 dB of return loss. What's your standing wave ratio going to be? Very low, I would imagine, and it is. Power to delivered to the load given input power and transmission line loss. Let's say I'm running 5 watts, and on my RG213 coax run out to my vertical, it's 75 feet. Let's say at on the 20 meter band, I'd be looking at 0.7 dB of loss. I wonder how much power I'm delivering to the antenna is arriving at the antenna. That'll tell you. If I'm running 100 watts on the 6 meter band, which my vertical covers, boy man, the line loss is going to be high at 50 megahertz. I have no idea what it'd be. Let's say it's 2.6 dB. Now let's say it's 2.3 dB. How much power out of that 100 makes it to the antenna? Only 50. Yeah, well, that. Okay. By the way, this is the third time through on this P4 quality film. I'm not a YouTuber, man. I don't have a lapel mic or whatever the heck they use. My Pythagorean theorem hypotenuse calculator. Why? Because my yard is 100 feet by 200 feet long. I wanted to see if I run a wire diagonally from corner to corner, if I'd be able to fit a 160 meter dipole up there. And sadly, not happening. So I figure, well, the backyard's a square that's 100 by 100. I wonder if I could get an 80 meter dipole diagonally in the backyard, because I have a couple big trees diagonal corners, and I see that I can, barely, but that's what I use this for. It's actually kind of handy. What else? Frequency to antenna link. Let's say I want to be able to transmit on 18.1 megahertz, okay? And I want to see what my options are. Well, these are the links for I wish I didn't do that. For a quarter wave, half wave, and 5/8 wave radiators for that frequency. And I wrote the spreadsheet so that it will display the result in feet and inches rounded down to the nearest eighth of an inch. Oh, what else? Radiator link. Let's say I've got a chain link fence that's 332 feet long, and my intention is to put a bunch of wood sticks on the top of the posts and run a wire down the length of that thing and transmit on it. Well, I could throw some counterpoise wires down and use it as a quarter wave, or I could wind a beast of an end-fed half-wave and get on the air in the AM broadcast band. Pretend I didn't say that. Well, that's pretty much what I use this thing for. Very, very handy spreadsheet. Very handy spreadsheet. I like it a lot. I was going to mention another thing that I do a lot with this, but I can't remember what I was going to say. I don't know how to lock this thing so it can't be saved. I don't know if you can with a spreadsheet. So when I quit the spreadsheet, I just tell it don't save. And that way it's a virgin sheet of paper when I open it again. Anyway, sorry about the horrible audio. Sorry about the horrible videos. So that's it. That's it. That's the amazing N8NK RF Toolz electronic numerical RF calculating machine.